Welcome, everyone. Today, we embark on understanding the fascinating concept of inductance, a cornerstone of electromagnetic induction theory. Recall from earlier lessons that when an electric current flows through a coil, it produces a magnetic field. This magnetic field links with the coil as magnetic flux. Importantly, this flux is proportional to the current producing it, which gives us the relationship phi b proportional to I. Now, imagine that the coil is tightly wound with multiple turns. Each turn experiences the magnetic flux, so the total flux linkage is the flux times the number of turns, expressed as NFB. Inductance is the scalar constant that connects this flux linkage to current through the coil. It does not depend on how the current changes over time, only on how flux and current relate for a given coil. Think of inductance as a magnetic inertia. It resists changes in current by producing an induced EMF opposing those changes. The physical nature of inductance depends solely on the coil's geometry, its length, area, number of turns, and the magnetic properties of the materials involved. Much like capacitance in capacitors depends on plate area, spacing, and dielectric properties. This relationship is fundamental because it reveals how electrical circuits can naturally oppose rapid current changes through electromagnetic interactions. Next, we'll dive deeper into types of inductance, mutual and self, building from this foundation. Let's deepen our understanding of inductance by looking at its physical and dimensional nature. Inductance is a scalar quantity, unlike vectors such as magnetic field or current. It quantifies how a coil resists changes in current by linking changing magnetic flux to induced electromotive force, or EMF. Its dimensions derive from magnetic flux divided by current, which is mass times length squared, per time squared, per ampere squared, expressed as ml squared t to the minus 2a to the minus 2. The SI unit for inductance is the Henry, abbreviated H, honoring Joseph Henry, who independently discovered electromagnetic induction alongside Michael Faraday. What's important to remember is that inductance depends solely on the coil's physical geometry, like how many turns it has, its shape and size, and on the magnetic permeability of the medium inside it. This dependence on geometry and intrinsic materials is very similar to capacitance, which depends on area, spacing, and dielectric constants. Physically, inductance behaves like electrical inertia, opposing sudden changes in current, much as mass resists changes in velocity in mechanics. This analogy helps us remember its role. Inductance tries to keep current steady by producing a back EMF that counters any rapid variations. Keep this concept in mind as we now explore two main types of inductance, mutual and self. Now, let's explore the important phenomenon of mutual inductance, where a changing current in one coil can induce an electric current or voltage in a nearby coil without direct electrical connection with Figure 6.12. Imagine two long solenoids placed one inside the other along the same central axis. These are coaxial solenoids. We denote the inner solenoid as S1 with radius R1 and number of turns per unit length N1, and the outer solenoid as S2 with radius R2 and N2 turns per unit length. Total turns in each coil are N1 and N2 respectively. When we send a current I2 through the outer coil S2, it produces a magnetic field which passes through S1. The magnetic flux produced by this current inside coil, S1, is represented by phi1. Since coil S1 may have many turns, the total flux linkage is N1 times F1. This flux linkage relates linearly to the current I2 in coil S2, with the proportionality constant named M12. the mutual inductance of S1 with respect to S2. The equation N1 phi1 equals M1 2 times. I2 expresses this elegant relationship. Understanding this mutual inductance is crucial because it forms the basis of transformers and many electromagnetic devices where energy is transferred magnetically across coils. Next, we will uncover how to calculate this mutual inductance and the physics behind it. Let's now calculate the mutual inductance for our two long coaxial solenoids in example 6.8. We start with solenoid S2, which carries a current I2. This current produces a magnetic field inside it given by the formula B equals the permeability of free space, mu 0 times number of turns per unit length, N2 times current I2. This B field is uniform inside the solenoid if it is sufficiently long, ignoring edge effects. The smaller inner coil solenoid, S1 with radius, R1 receives this magnetic field. The magnetic flux through S1 is simply the magnetic field times the cross-sectional area of the inner coil, pi r1 squared. Since solenoid S1 has N1 turns per unit length and length L, the total number of turns is N1 times L. The total flux linkage, then, equals this number of turns times the flux, giving us N1F1 equals N1L multiplied by pi r1 squared times mu 0 N2I2. From the definition of mutual inductance, we rearrange to find M12 equals N1F1 over I2, which results in mu 0 N1N2 pi r1 squared L. This formula neatly summarizes how mutual inductance arises from coil geometries and the fundamental magnetic constant mu 0. Remember, this derivation rests on the approximation of ignoring magnetic field variation near coil ends and assuming uniformity, an assumption valid for long solenoids where length far exceeds radius. We'll soon explore the reciprocity of mutual inductance next. An important and elegant property of mutual inductance is its reciprocity, meaning the mutual inductance M12 of coil 1 with respect to coil 2 equals M21. The mutual inductance of coil 2 with respect to coil 1. This symmetry can be mathematically demonstrated for the long coaxial solenoids we just discussed. When current flows in the outer solenoid, it creates magnetic flux through the inner solenoid. Conversely, a current in the inner coil also produces magnetic flux threading the outer coil. Despite different coil sizes and arrangements, the mutual inductance remains the same from either side. This reciprocity holds true quite generally for a broad range of coil geometries and configurations. It's especially valuable in cases where it's hard to calculate the flux due to one coil inside another directly. Knowing the symmetry lets us find one mutual inductance and infer the other. This mutual behavior also indicates that energy transfer and magnetic coupling between coils are symmetric, supporting fundamental physical principles related to conservation of energy and electromagnetic induction. With this understanding, we can confidently analyze more complex coil systems and their mutual interactions. So far, we've assumed our coils are surrounded by air or vacuum. However, the medium between or inside coils can significantly influence inductance. Specifically, when the coils are filled with a material having relative permeability MUR, the magnetic flux is enhanced. This relative permeability μr multiplies the permeability of free space μ0, increasing the magnetic field and thus flux linkage. Replacing μ0 with μr μ0 in our mutual inductance formula reflects this change. Im equals MUR μ0 N1 N2 pi r 1 squared L. This enhancement is utilized in devices like transformers, where soft iron cores with high permeability dramatically increase mutual inductance, allowing more efficient energy transfer. Besides material properties, mutual inductance depends on how coils are oriented relative to each other and their separation distance. Intimately linked coils arranged optimally maximize magnetic coupling, while coils far apart or poorly aligned have smaller mutual inductance. This interplay between materials and geometry makes inductance engineering a versatile tool in electromagnetic device design. Next, we'll explore self-inductance, the related phenomenon occurring within single coil. Turning our attention inward, let's discuss self-inductance. Unlike mutual inductance involving two coils, self-inductance describes a coil inducing an EMF within itself when its own current changes. Physically, current through the coil creates a magnetic flux linking that coil's turns. This flux linkage is proportional to the current I, expressed by NF subscript B equals L times I, where L is the self-inductance or coefficient of self-induction. When the current varies with time, the flux changes, inducing an EMF within the coil that always opposes the change, following Lenz's law. Mathematically, the induced EMF equals negative L times the rate of change of current. Epsilon equals minus L di over dt. This opposition to sudden changes can be thought of as the coil's electromagnetic inertia, analogous to mechanical inertia, resisting velocity changes. The self-inductance depends entirely on the coil's geometry, its length, area, number of turns, and the magnetic permeability of the core material inside the coil. Understanding self-inductance is key to analyzing behaviors in circuits with inductors and transformers, and will prepare us for analyzing energy storage in magnetic fields. Let's calculate the self-inductance of a widely used geometry, the long solenoid. Consider a solenoid with cross-sectional area A, length L, and number of turns per unit length N. When current I flows through it, a magnetic field B arises inside, approximated well by B equals mu0 times N times I. Edge effects at the ends are neglected since the solenoid is long compared to radius. The total flux linked with the coil's turns is NFB, the total number of turns NL multiplied by the magnetic flux per turn, which equals the magnetic field times area A. This flux linkage comes to mu0 n squared ALI, revealing a neat quadratic dependence on turns per unit length. Dividing flux linkage by current gives the self-inductance. L equals mu0 n squared AL. This formula shows how coil geometry dictates inductance, a key design consideration in electromagnetic devices. If the solenoid's core is filled with a material of relative permeability μr, like soft iron, the inductance scales up by μr, becoming L equals μr mu0 n squared AL. The increased magnetic flux due to the core material's enhanced permeability means more energy storage and stronger opposition to varying currents. Understanding these dependencies empowers us to tailor inductors for specific electrical and magnetic behaviors. The self-induced EMF inside a coil is often called back EMF because it pushes back against any change in current. This characteristic is essential. It means the coil behaves like it has electromagnetic inertia, akin to how mass in mechanics resists acceleration. To understand this analogy, think about how the coil opposes changes in current by generating a voltage that tries to maintain the previous current flow. To increase current in the coil, work must be done against this back EMF. The rate of this work done or power is the induced EMF magnitude times current. dW over dt equals the absolute value of epsilon times I, simplifying to L times I times di by dt by substituting the EMF formula. Calculating the total work done to build up the current from zero involves integrating this differential energy, leading to W equals 1/2 L times I squared. Remarkably, this expression mirrors the kinetic energy formula 1/2 mv squared, making L the electromagnetic analog of mass. This stored energy resides in the magnetic field around the coil and can be returned to the circuit. Understanding this magnetic energy storage is vital for analyzing circuit behavior involving inductors, transformers, and energy conversion. So far, we know the magnetic energy stored in an inductor is half the product of inductance and squared current, or U subscript B equals 1/2 Li squared. Let's express this in terms of magnetic field inside a long solenoid, which connects more directly to physical space with example 6.9. From the solenoid magnetic field formula, current I equals B divided by mu0 times N, where B is the magnetic field, mu0 is permeability of free space, and N is turns per unit length. Substituting I into the energy formula gives U subscript B equals 1/2 L times the square of B over mu0 squared N squared. Since the inductance L itself is mu0 N squared AL, substituting this cancels N squared and 1 mu0, simplifying to U subscript B equals 1 divided by 2 mu0 B squared AL. This final expression tells us the energy stored equals magnetic field squared times volume A times L, divided by twice mu0. Put differently, the energy density, energy per unit volume, stored in the magnetic field is U subscript B equals B squared over 2 mu0. This parallels electrostatics, where energy density depends on electric field squared. This formulation is powerful for analyzing magnetic energy in various devices and preparing for energy comparisons with capacitors. Let's conclude by comparing energy storage in magnetic and electric fields, revealing beautiful symmetry in electromagnetism. The magnetic energy density, energy stored per unit volume in a magnetic field, is U subscript B equals B squared divided by 2 mu0, where B is magnetic field and mu0 is magnetic permeability of free space. In contrast, the electrostatic energy density inside a parallel plate capacitor is U subscript E equals 1/2 epsilon 0 E squared, with E as the electric field and epsilon 0, the permittivity of free space. Both formulas depend on the square of their respective field strengths, underscoring the fundamental duality between electric and magnetic fields. This equivalence reflects Maxwell's unified theory of electromagnetism, uniting electrical and magnetic phenomena using these constants. Physically, this relation means energy is stored not just in charges or currents, but in the fields permeating space. Recognizing this equivalence guides advanced electromagnetic device design and deepens understanding of energy flow in circuits. With these insights, we have covered inductance's definition, calculation, energy relations, and its role linking electrical and magnetic domains flawlessly. To wrap up, today we have developed a comprehensive understanding of inductance. We began by framing inductance as the proportionality between magnetic flux linkage and current, introducing mutual inductance between coils, which depends on coil geometries, their relative positioning, and the medium's magnetic permeability. We proved the powerful reciprocity that mutual inductance is symmetric. The flux induced by one coil due to the other's current is equal in reverse configuration. Moving into self-inductance, we saw how a coil resists changes in its own current by producing a back EMF, functioning like electromagnetic inertia, mirroring mass in mechanics. This property plays a crucial role in circuit behavior by smoothing current variations. We also formulated the energy stored in inductors as magnetic potential energy, expressed through 1/2 Li squared, or equivalently in terms of the magnetic field squared, and volume of the coil. Lastly, we compared magnetic and electric energy densities, reinforcing the unified nature of electromagnetic phenomena. These core concepts create a strong foundation, leading to the exploration of transformers, energy transfer in RL circuits, and complex electromagnetic device design. Well done for engaging with this challenging and deeply rewarding topic.